Hey everyone. Believe it or not, this is the third time I'm doing the teaching, but I think I figured out how to deal with the iPhone and Zoom and the recording. Kind of tired, but okay, so what I want to do is I'm walking you through how to do each of the problems for homework 19 and homework 20. And this might be a great way for me to do this in the future, not just post the solutions to the homework, but also talk you through it. So I'm hoping it's in focus as good as it could get. So we're looking at this first problem. It's number 4. It says, for the beam, determine the reactions at A and the tension at BC. So we basically have a beam. It has 5 external loads. We have a pin connection at A, which means I have a force in the X and force in the Y. And then I also have a tension here in the cable. So when doing my table, I see I have 5 forces that I know everything about, and then an AX and an AY, and then a tension at B that I don't know. So I have 3 unknowns. It's a 2D problem. I need to analyze one body. So I'll draw the free body diagram of the bar with all the forces on it. And that's what I have right here. I have my bar with my 5 known, my AX, my AY, and my tension. And all the forces are in X and Y, so I don't need to find components. They're already given. And then I'm going to look at what would be the most efficient way of solving this problem. Which equation do I want to do first to find one unknown? And I could do sum of the forces in the X equals 0. So AX is equal to 0. And then I did some of the moments about point B to cancel out T so I could find AY. And then I did some of the forces in the Y to find T. And then in the end, I decided to do a check. I did another moment equation about any point, and I substituted in my values for A, Y, and T, and I got the sum of the moments equal to 0. So in that case, I was able to check my work. Okay, the second problem that was assigned was the one with the boom and the tractor right here. And we have 3 forces, 3 external loads that are given. And in the problem, it says this W is 25 kilonewtons. They also tell you what the tension is in the blue cable, and the tension is 25 kilonewtons. And what they're asking you to find is the tension in the rod CD, and also they want to know what the reactions are in the pin. So if you just jumped ahead and started to draw a free body diagram of this whole thing, you really would have wasted your time. Because the fact that you have to find the tension in CD and the reactions at the pin, you really need to make those forces external. And the best way to do that is to choose your body for the free body diagram of only the boom. So we had 3 unknowns, 2D problem, choose the boom. And when you choose the boom, you get a free body diagram that looks like this with the 3 given tensions, right? There's that tension. It made the tension be an external support, an external load. And then here's the other tension you have to find, and there's BX and BY. And then I choose which equation has with one unknown, and BX, sum of forces in the X give you BX is equal to 0. And then I did a sum of moments about point B to find what TCD is. And then I did some of the forces in the Y to find BY. And then I did a check by doing a sum of the moments. So the difference between these two problems, the original just beam problem, this is, a pretty simplistic problem. But the difference one here is you had to choose which body you wanted to analyze. So the ones that were unknowns were actually external forces. Okay, the third problem on this homework was 33. We have a bracket here that has an external force of P, which is given. And then we have a pin at D, so that means we have a DX and a DY. And they want us to find the forces, the reactions at the supports, and they want us to find the tension. Again, the problem is very similar to the other, but there's another new feature. Basically, you have three unknowns. You need one body. You're going to choose this L bracket. But the different thing here is that the tension is coming off of A and it's coming off of E. So when you draw this free body diagram, you have to make sure that you have the tension coming off A and E. So in that case, here's my free body diagram. Here's my L bracket. I have my tension coming off here and here. And we know they have the same magnitude, but I'm calling them different tensions because you'll see in a minute. And then I have my dx and dy, the reactions at the pin. After the next step after drawing a free body diagram is to find components. And in the previous problems, all the forces were in the x and y. But this T1 here is not. So I find my components of T1. I do my unit vector check and my visual check. And then I start deciding which equations I want to use. And again, I'm going to do it most efficiently. I chose to do some of the moments about D because then I could solve for T. And then I did some of the forces in the X and I got dx, and I did some of the forces in the Y and I got dy. And then I did another sum of the moments equation to do a check to make sure that they were all correct. And then the fourth and last question in that homework assignment is about this boom here, this rig. Let me move it. This rig, they said, is welded here and it has a fixed support. And we know at fixed supports, it has a force in the X, a force in the Y, and a moment. We have a weight given. We have another weight given of 3,600. And then we have a tension here. And the tension is also given as 4 kips, which we know a kip is 1,000 pounds. So we have three unknowns here, 2D problem, need to find one body. The body you're going to analyze is this boom. Now, they have two scenarios. The first scenario is they want to have the tension anchored at F. So when you draw the free body diagram of the boom, there is another problem. Okay, well, we'll come back to that one. Let's do this one. So in 43, we have our boom and we have our two forces coming off, and we also have our tension here. And then we have our three reactions at the fixed supports. Okay, all the forces are in X and Y, so I don't need to find components. So the first equation that would be best to find them is sum of the forces in the X, and I get EX to be 0. Sum of the moments, what's the next sum of the moment? I chose to do some of the moments about point A. Maybe that wasn't the greatest point. Maybe I should have chose to do some of the moments about E. But in any event, I chose to do some of the moments about A, and I found that the moment about Z is negative, which totally makes sense because these two forces here are trying to twist. They're causing a positive moment on this, and the T is causing a negative moment, and these loads and the moment it causes is greater, which means that point E has to be resisting it going in the other direction. I drew it positive, but I got a negative. And then I did a sum of the moments about another point just to check it. Actually, I wound up doing the sum of the moments about 3 points to get the same value of that moment. So I did a super check. Part B is telling you to connect the tension somewhere between B and E. And the reason it doesn't tell you where to connect it is it doesn't matter, because now the tension, once connected, is an internal force, and you're not going to get a moment due to that tension. So we're only going to have these two external forces pulling on this fixed support. And I did some of the forces in the Y to get EY, did some of the forces in the X to get EX to be 0. And then I did some of the moments to get this moment. And then I did a check as well. Okay. And there was another problem. The other problem was 35. So let's go to 35. There it is. So 35 has a bar, a roller, and a roller. And then let's see, from B to D, it's a cable. So it tells you that there are two 400 Newton forces And since it's a roller, we know there's a normal at A and a normal at C. And it's asking us to determine the tension in BD and the reactions at A and B and C. So we draw up our table. We find that the tension is an unknown and the two normals are unknown. We have three unknowns, three equations, need one body. We choose this diagonal body. We draw our 400 Newton forces on the two normals coming, one going up and one to the side. And then we have our T, and T has a component in the X and Y. So I'm going to solve for next, after the free body diagram, the components for T, Tx and Ty. And then I notice from here, whether I do the sum of the forces in the X equation, the sum of the forces in the Y equation, or the sum of the moments about any point, I'm going to get more than one unknown in the equations. So I'm just going to do the easy ones first. Sum of the forces in the X, sum of the forces in the Y. That gives me equation 1 and 2. I'm going to move this up a little. Sorry, hang on. So we have some of the forces of the X give us equation 1. Some of the forces in the Y gives us equation 2. And then I did some of the moments about B, and you notice that I did actually make an error. In order to find the components of T, you had to do similar triangles, and I made a mathematical error here. So, but I did copy it and posted the solution. So from these three equations, I did a matrix, and I found out what these values are. And this made me very happy because I know the direction of normals and tensions. I should get values positive. If I got negatives, it would have meant I made a math mistake. And then I did go on and do a check. I went on and did a check, and my check came out to be 88 equals 0. The fact I'm dealing with numbers in the hundreds of thousands, I'm imagining this was just a rounding error. But anyway, so that's homework 19. The 2D problems. And now we're going to go on to homework 20. So in homework 20, the first problem was the plate problem. Let's find it. Yeah. So in problem 97, we're looking at this figure and it says it's a 20 by 20 inch square plate and the plate weighs 56 pounds. So that means that the weight is going to be centered in the middle going down. And then we have three tensions, and take a look at this. Notice that point A is at the midpoint of this side of the plate. And then B and C are at the same dimension in the X from A and in the Z from A. So it's actually like an isosceles triangle. So odds are the tension of B and C are going to be the same because they're balancing out that because the weight's going to be in the center. So we have three tensions that are unknown. They gave us the weight in the center. We need three equations. Here's my free body diagram. I decided to do some of the moments about Z that gave me one equation. I did some of the moments about X, it gave me another equation. And then I did some of the moments about, then I did some of the forces in the Y, and it gave me three equations. What's interesting, the interesting feature about this problem is even though this is a three-dimensional problem, there is only a sum of the forces in the Y equation. There are no forces in the X or the Z, so those two equations don't even count. And because the forces are all in the Y, there's no sum of the moments about the Y. So even though it's a three-dimensional problem, there really only are three equations possible. And from these three equations, I could either substitute three equations, three unknowns in the calculator or in the matrices, and then I get these three values. And again, I'm very happy that they're all positive. It means I didn't make a mathematical mistake. And sure enough, TB and TC were the same. Okay, so that is the first problem in 20. Now let's look at the second one. The second one is using the same picture, but now it's saying, just hang on, let me just read it again. Still has the same weight, supported by three wires. Okay, so this problem 98 is saying now assume all the tensions are the same and the weight of the plate is still 56 pounds. And now we want to find a weight, the weight of a block that we put somewhere here and its location to balance this out so that the tensions are all the same. So looking at this problem, we know all the tensions are the same, so that's one unknown. We have a weight that's given, weight of the plate, but now the weight of the block we don't know, and we also don't know the location of the block on the plate. So we don't know the distance in the X or in the Z. So really in this problem, we have 4 unknowns. Even though it's a 3-dimensional problem, we found we could only have 3 equations available. So this happens very often in engineering where there are more unknowns than the number of equations. That problem is called indeterminate. You can't solve it. So in real-time engineering, you have to make some assumptions. And if we look back at these 3 forces, well, let's look back at the picture. If we look back at the picture, if this is symmetric, if B and C are symmetric about A, the most probable thing, well, what's going to happen is in order for these tensions to be the same, that block is going to have to be somewhere in the midpoint. It's going to have to be along line A. So my assumption is that the distance on the Z to this block that we're going to place on there has to be 10. So I made the assumption that RZ is 10. So now I have all my tensions being T, so that's one unknown. I have WB as an unknown. I know RZ is 10, but RX is an unknown. So now I reduced it to 3 unknowns. I need 3 equations. I ran the 3 equations, some of the forces in the Y, some of the moments about the Z-axis, some of the moments about the X-axis. And let me just tell you, it's an algebra nightmare to solve this problem. So I probably should have never picked this as a statics problem because I want you to get better in statics. I don't want you to be wasting your time with all the algebra. I'd rather you spend the time on statics. So I wound up solving it and I found out what the values are in here. But basically, I would say, as long as you understand why I made this assumption and you got the 3 equations correct, just quit the problem. Okay, next problem, 106. 106 is right here. There's a pole. It has a ball and socket joint here. It has 3 forces on it. And notice the 3 forces that are on it, 2 tensions and 1 an external load. They all have components in many directions. So we know we're going to have to do components. They mention it's a ball and socket joint, which we know it only has 3 unknowns and 3 forces, a force in X, Y, and Z. And then we also have to find out what the tensions are. So we have 5 unknowns in this problem. So put up my table. I have 5 unknowns. I need 1 body. I drew a free body diagram of the pole. I drew out my 455. I drew my reactions at support A of AX, AY, and AZ. I drew my 2 tensions. And then I went through and found the components of 555 and each of the tensions. And I did my visual check and I did my unit vector check, and it continues on the next page. And then, since there's so many forces, I just went ahead and I solved for what the sum of the forces in the X are, Y, and Z, because none of these equations are going to have 1 unknown in it. So I have equation 1, 2, and 3. But remember, I need 5 equations. So the next equation I'm going to have to do is sum of the moments. And you guys could decide where you want to do moments, but I chose to do moments about point A because first off, these 3 forces don't create a moment. Plus, we have our axes that are going through A, and notice all these forces go through the y-axis. So they're all intersecting the y-axis. There is not going to be a moment in the y. So I solve for the moment about A in 2 ways. One, the way I always like to do it with right-hand rule, and you could see that how many of them cross out because they're parallel or they intersect. But then I also did it the way some of you still like, where you do it vectorially. So I solved for the moments about A, R cross the three F's. And in the end, I got the moment about a moment was this. And notice there are moments about the x-axis and moments about the y-axis, z-axis rather. No about y-axis because all the forces intersect the y-axis. And now here's my equation 4 and 5. So now I have 5 equations. I plug it into a calculator. I could do it by matrices if I want, or I just do it by systems of equation, and I get my answers. The thing I want to point out to you is we look at this ball and socket joint. It has an X of 195, a Y of 1170, and a Z of 130. That means it's being pulled in 3 directions, right? And we got positives for all of it. So, but the resultant force, this ball and socket joint is really being pulled. Ball and socket joint is really being pulled into that positive octant, right? So when I think about ball and socket joints, well, I have to order one. I have to decide what kind of ball and socket joint I need. And I'm going to have to get one that could resist the forces. You might look at these forces and say, okay, the ball and socket joint needs to resist a maximum of 1170, but that's not correct. Because the magnitude of the force that is really at that ball and socket joint is the square of each one. And it comes out to be 1193. So that ball and socket joint really has to be able to resist 1193 newtons. And as an engineer in the design, if you decide you want a factor of safety, a safety factor of 5, you're going to really have to choose a ball and socket joint that can withstand more than 5,000 newtons. Okay, we have one more problem. And this problem is 114. And here is 114. We have a bent bar. We have a cable. We have a 400 Newton pound, 400 Newton force. And we have 2 connections here. So we read it and it says it's a bearing. Well, that's not really helpful. It really didn't give you all the information. So when we look at it, it looks like it could be a journal bearing. It might be the ball bearing, which Rob calls a spherical bearing, which is way better. I don't think it's a thrust bearing because I don't see any little collars on the side. But basically in the homework, I mentioned that treat these 2 as a ball bearing or a spherical bearing. And in that case, the only reactions are in the Y direction and the Z, because that's what it could resist. So we have 2 unknowns here, 2 unknowns here. We have an unknown in the tension, and we have 1 known force here. So that's 5 unknowns. 5 unknowns. We need 1 free body diagram. So we draw a free body diagram of the bent bar. We draw a tension, and we needed to use a little bit of geometry to actually find out the geometry of this tension, so we could go ahead and find the components of the tension. And then I did my check too. So I have my bar, I have my tension. I wound up doing some of the moments. First I did the forces. I did the sum of the forces in the Y and the sum of the forces in the Z. So I got equation 1 and 2. And then for some reason, I decided to do some of the moments about B. The reason I chose it is I like to pick a point where the axes are. It made it easier for me, but some students did it about C or D, which might even be a way better idea. In any event, you could do it wherever you want. I did it using right-hand rule. I determined that the sum of the moments in the X, Y, and Z from here, I added up all the X's, added up all the Y's, added up all the Z's, and I found that from some of the moments about B in the X, I got a value for that 1 tension. So now I have equation 1 and 2, equation 4 and 5, and I use these equations in the calculator with systems of equations or with matrices, and I found these values. Okay, and the same thing occurs with D and with C. I need to know what load these bearings could take. So when I look at C and Y and CZ, I really should get the resultant, hang on, let me find my pencil. I should get the resultant of what C is actually experiencing. 336 squared plus 467 squared under the radical. That turns out to be 36 squared plus 467 squared under the radical. Oh, let's try it again. 336 squared plus 467 squared equals under the radical. It comes out to be 575.3 newtons. That means that when I choose a spherical bearing at C, I have to make sure that it can withstand a load of 575. So I have to pick the material and the size of the bearing that'll support this. And for D, same thing. Okay. All right. Thanks. Bye.